Right, just a quick recap. We have definition of group on the backboard. We have a proof of this. H is a subgroup of a group if and only if AB inverse belongs to H for all A, B, and H. Why is that an important thing to prove? Why would anybody want a statement like this? I call this a checkability theorem because proving something's a group, as you probably already saw, is a pain in the butt. You have to sit there and go through every property and check them all. And if you have something that makes it easier, that would be great. I don't want to mess up your computer.
No, I'm just trying to give you more swag. Sorry.
So that's why I call this a checkability theorem because it gives you a quick way to check if something's a group or not. And you had the same thing for subspaces in linear algebra. They gave you those two criteria that the scalar multiples of vectors had to remain in there and the sum of two vectors had to remain in there so that you quickly can check whether something's a subspace or not. So it's similar to that idea. Jake?
So like, I'm confused about like where the connection between like H and G is in that sentence. Like they already assumed that like
so, yeah,
A and B is in G. Already.
A and B is in H.
But H is in G, right?
H is in G.
But like that's like assumed before you.
Yes. So I think I gave you the full statement last time. So. And I should be saying as I'm going along, see, right here.
So if we were going to write like a K proof of this, we want to start off with the definition of subgroup.
No, I think that would make it hard to read. You could probably just say subgroup and then, that would be something you'd refer the reader to, just like I'm doing here. But I put the definition back there so that we could go back and look at it because I felt some discomfort in class. And I felt some discomfort when I looked at your homework of what that definition is. It's just a set that satisfies those properties. So a reference card. But when someone says subgroup, it's kind of universal. Everybody knows that's a universal definition. Okay, so the first step was that we were going to prove one direction. So our no is that H is a subgroup. That means all those properties on the backboard hold, with G replaced with H because it satisfies all those three things. And my show is to prove that A star B inverse belongs to H for all A and B and H. And that's how I cover my butt. Then the first claim is that B inverse belongs there, and so I look over in the chart and say, how can I say such a thing? Well, number 3 tells me I'm allowed to say that, so that's my hypothesis. Remember in your proof that in your checklist, you have to state where the hypothesis is being used? When I say no, it's the hypothesis being used. The second claim is that I'm kind of done, that this product now belongs to H, and that's true by the closure property, which is property number 1 that's written up on that blackboard. And so that proves that easier direction. Good? It's bad if someone, can I do this? All right, so the second part of the proof. Save the best for last. This direction. I showered. I wore deodorant.
It's all good, Matt.
Okay, the no and show reverse itself. I think Ariana said that when she had an if and only if proof. You guys all think you had it bad. She had it bad. She had 2 proofs to do for her WPR. So she's like, oh, I just reverse them both. Whatever was first in my no becomes my show. I can just erase no and put show there. And whatever was my show becomes no. So I just reverse the order. So this is why I saved this for last. It's more annoying. You have to go through that checklist, all except one. Which one don't you have to do? Associative. I'm shorthand writing this.
Why aren't you effective associative?
Because it's already it's inside a group already. So if
that's
there's
like
three
part of it.
elements inside the set H, by the property of associativity in G, this automatically comes down. The other ones don't automatically come down. You can make a subset. You could make a subset H in G with the E sitting out here. There's no guarantee that the E is in here. And it could be the case that A is in here and A inverse is outside. So that you have to verify. And it also could be the case that you have A is in here, B is in there, but when you multiply them or product them, it's going to go out. So those are the three. And I put them in order of difficulty because I always do the easy stuff first. All right, so the first thing I'm going to show is the E stuff. So why is this true? Why can I say this? The only thing I've got in my no is one thing. And I've done a little bit of George Foreman here, so it might be confusing. So if in my no, I have this thing, right? This is true for all A and B.
Oh, okay,
So I could replace this for A and this for B. And then by my no, it says that that belongs to H. And I made this especially confusing because I just did a George Foreman. So this is okay and legit to write. It just makes it confusing to the reader what's going on. Right? Maybe to clarify it, I should have put something like this. And then said with it, capital A is equal to, and then capital B is equal to. That would have made it much more clear. Or use completely different letters over here and then do a substitution. That would make it very clear to the reader. Agree? Okay, so I think there's something on your fill-in sheets that asks you specifically why I'm allowed to do this. Yes? And now I'm going to drop some stuff. Well, I'm going to do one maneuver, which probably needs some justification. This inverse coming in, it rotates the order, and you guys probably did this in linear algebra when you had A times B inverse. It's B inverse A inverse. It switches the order, and it's a very short proof to prove that. I'm going to use it. Someone like Dr. Williams would probably want to see that detail in there. Someone like Emily would probably put that in the appendix because it's detracting to see the proof of that right here. I'm using that. And that's actually pretty simple to show. You would just have to show that if you have a product, then if you multiply by that guy, that turns you to E. So this is the legit inverse. That's the definition of inverse. Number 3 is that definition. So I think I wouldn't have told you that unless I made the sheet. I realized, oh, well, I'm just doing this. And so it's something that some professors will want you to prove. Some professors, right? I'm not a good teacher for this because of that. I don't have that much attention to detail.
I don't understand what we're doing now.
I thought that we didn't know, like we didn't specify what this like star operation was.
Yeah, we didn't.
Okay, so this applies for any operation.
Yeah, I'll prove that for you in 2 seconds after we're done. So I'll give you my appendix.
So like, even if it's addition. Or,
yeah, it's true.
Okay.
So I'll show that for you.
I don't get what we're doing.
All right, so I'm trying to show this first property that the identity is in there, right? So all I have to work with is this thing right here. So I'm going to do this maneuver, and you can already see what's going to happen. If I drop off the inverses here and then apply the associative law, I'm going to get E.
I don't get like how you're just like why are you just multiplying them together now?
Why am I doing this? Let me show you 2 more steps, and then it'll become clear why I'm doing this. So B inverse inverse is B. Again, that's something that someone should actually prove, maybe, like if they had a clean proof, they should prove that.
I remember I spaced out. You should prove what?
Right here, B inverse inverse is actually B,
Oh, okay.
right? If you had Dr. Dongan for linear algebra, he might have happily proved that, actually. He might have been joyously proving something like that. So I can show you how that works too. It's not that hard. But so it should probably prove. So I think that's on your sheet too. That's something that should be a detail that if you're turning it into Dr. Williams, it should probably be in there. And then I'm going to take off those parentheses and use the associative law. It's the associative law applied several times, right? I'm moving the parentheses around, and then you can see things drop out. This becomes E. This becomes the inverse. This becomes E, and you get E. Okay, the E is the identity. The definition of identity is it leaves things unchanged. So it's like, it behaves like the number 1. So it's gone. So it disappears. I get this. And inverses, if you go back and look at that chart back there, the inverse leaves things on 2E. So A star, A inverse is E. So I get this. So that's why I did this. If this guy belongs to H, and I did all this
What
algebra,
did you do with your B's? So the B's are.
So B inverse times, or B inverse
Yes.
star B would be the identity.
so right here, from this step to this step, there's one arrow going over. B star B inverse is equal to E. By property of inverse. So I have the reason right here.
So is that using the associative property?
Taking out the parentheses is using the associative property, right? Because the parentheses don't really matter. That's really what the associative property says. So it's multiple steps of the associative property. The second thing is I'm using all those things back there by definition. Like, what does inverse mean? It does this. What does identity do? It does this. So I'm using the definitions of identity and inverse to do these maneuvers.
Why do you have to do it again with the A's? Like, isn't it just enough that you have an E to begin with from the B's?
No, because I still have the A and A inverses sitting on the
Yeah,
outside.
because you're proving that E is an element of H, and if you have the H there, then you didn't prove that.
I want to get down to E. My goal is to use this property here to show E as an H.
So imagine like H is on the right hand side of the equation, right? On the left hand side, you have the A's and the H. So now you have
Yeah, but you already know A's are in there, so why can't you just say with the A's?
Why did I have to do this last step?
Yeah.
Because I want to make it very clear to the reader that the final answer I get here is E. Because I started out with something that belongs to H, and they're all strung out by equal signs, and my last answer I get is E. That proves, recall that I'm trying to prove E as an H. So going back, I'll do a quick summary. Quick summary. I started out with my no, taking, it said that if I have A and B and H, then this property is true because it's part of my given that A star B inverse is an H. That's by the no. And because A star B inverse is an H, then I can reapply that one more time, my no one more time. So I can just let this be my new A, and let this be my new B. Well, sufficiently lost? Are we lost? So this is all I have to go on, right? So if I start out with an A and a B and H, then all I know is A star B inverse is an H. If I know A star B inverse is an H, I can reapply that again and say A star B inverse star A star B inverse inverse is an H. So it's two applications of this rule that led me to this statement. See, I told you I'm going to have gaps. Jenna? Good? Right, there's like a little anonymous thing on your sheet, so let me know if you got it or if there's a piece that you're confused by.
I think it's, the only thing that's confusing is like, the mental lead to do that. Like,
Yeah, I just realized I left out that detail. Yeah, I left out that detail right there, right? That I'm applying this property twice. I'm saying let's start out with an A and B in there, then A star B inverse is in there by no. If A star B inverse is in there, I can let capital A be A star B inverse and capital B be A star B inverse and apply it again. And that's what leads me to that line. Good? Good? All right.